Hello, everyone. Welcome. I am Jet Aguilar from the Astronomical League of the Philippines, and I will be hosting this webinar. Thank you so much for joining us for our 2023 Astronomy Expert Speaker Series online lecture series for today. I am very happy to see a lot of registrants attending, especially for today's webinar. I was pleasantly surprised to see that we have a record-breaking 330 plus registrants from all over the world. Thank you so much for attending, and thank you also to those who have joined all our past webinars. Today, we are very fortunate to have with us none other than the current president of the International Astronomical Union, or the IAU, Dr. Debra M. Elmegreen. Dr. Elmegreen will explore the composition and structure of galaxies across cosmic time, probing the evolution of galaxies as they grow and interact with one another. My fellow ALP member, Ms. Imelda Joson, will be doing the introductions for our esteemed speaker later. For those who were not able to register, but would still want to watch this ongoing webinar, we are currently live streaming on Facebook at the Facebook page of the Philippine Astronomy Forum. Before we start, kindly allow me to explain some rules for this webinar to help us make this an enjoyable learning experience for everyone. Please listen and do your best to give your undivided attention to our speaker. There will be a short question and answer session at the end of the lecture. You may type in your questions under the Q&A tab found in your Zoom interface at any point during the presentation. We will do our best to read and answer your questions live after the lecture or via the Q&A tab. We would like to remind everyone that the contents presented in this webinar will remain as the individual property of the lecturer and the photographers in the presentation. We will also be distributing certificates of attendance via email to all registered attendees who will be present with us throughout the webinar. So please use the name you have written in your registration forms to help us facilitate this process. Enjoy the webinar and let us all have fun learning. Here's the program flow for the webinar today. And now I would like to turn you over to Mr. James T, the President of the Astronomical League of the Philippines, to give his welcome remarks.
Good evening to our viewers in the Philippines, and good morning to our guests in the United States and Europe. My name is James T, President of Astronomical League of the Philippines. On behalf of ALP, I would like to welcome you all to our Astronomy Expert Speaker Series 2023. This webinar is part of the ALP's International Astronomy Educational Outreach Program. Our goal is to bring renowned experts and scientists to the Filipino people and to the rest of the world. So that is why the webinar is being offered free to the general public. I would like to take this opportunity also to thank ALP members who have been instrumental in putting this program all together, especially to Imelda Joson, Edwin Aguirre, Jet Aguilar, Jun Lau, Kendrick Colty, Andrew Ian Chan, and Peter Benedicto Balinal. So this will be our 30th lecture in our speaker series. Our speaker for today is no other than Dr. Debra M. Elmegreen, the current president of the International Astronomical Union. We have more distinguished speakers lined up in the coming months, so please stay tuned. And please do not forget to register in advance for this future webinar. Thank you very much. And I'd like to turn over the program to Imelda Joson, who will be introducing our guest speaker for today.
Thank you so much, James. Before I give the introduction to today's speaker, I would like to give a special thanks to none other than Jet Aguilar, Dr. Jet Aguilar. Unbeknownst to many of you, Dr. Aguilar is actually a surgeon, and not just an ordinary, surgeon, but he is a brain surgeon, a neurosurgeon. And he has been helping a lot of people in the Philippines, and also he has been funding this Zoom webinar that we've been doing. So aside from being the MC and moderator, he is the one sponsoring the Zoom subscription. And today, I didn't expect him to be here because, it has been a long day for him, 7 hours of surgery, but yet his dedication, his passion for this outreach program is something to be commended. Jet.
Thank you.
Thank you
Oh,
for
thank you.
that.
Thank you so much, Imelda. But I would not really miss the Dr. Elmegreen's lecture. Thank you. That's why I'm here. Thank you.
Yeah. So going back to our speaker, almost 11 years ago, while Edwin and I were at the AAS meeting in Alaska, we met a very special couple. I can distinctly remember that day when we walked to a meeting room and the tune of Claire de Lune was playing. Unbeknownst to us, the couple we met that night, Debbie and Bruce Elmegreen, will inspire us so much and later become friends with. Just like Edwin and I, their marriage is a match made in heaven because they too are both in the field of astronomy. That more than the force of gravity, they too are bound by something more powerful than the forces in the universe, that is, love. Both have achieved so much in the respective fields of studies, that is stellar evolution and galactic structure. Both are graduates of two prestigious universities, Princeton and Harvard, yet both are so down to earth. Today, Debbie will give us a glimpse of galaxies at the dawn of the universe. Dr. Elmegreen was the Professor of Astronomy on the Maria Mitchell Chair at Vassar College from 1994 to 2022, after joining the faculty in 1985. She received her undergraduate degree from Princeton University, the first female to major in astrophysics, and a Ph.D. in astronomy from Harvard University, and was a Carnegie Observatories postdoctoral fellow, the first female to hold this position. Her research focuses on the structure and evolution of galaxies at optical, infrared, and radio wavelengths. She enjoys observing with the Hubble Space Telescope and now with the James Webb Space Telescope. Dr. Elmegreen is president of the International Astronomical Union, the first U.S. female to hold this position in its 103-year history, and past president of the American Astronomical Society. She received the National George von Brisbrook Prize for service to astronomy and is an elected fellow of the American Academy of Arts and Sciences, the American Association for the Advancement of Science, and a legacy fellow of the American Astronomical Society. Ladies and gentlemen, it is with great honor that we have Dr. Elmegreen speaking to us today. Debbie?
Thank you, Imelda, for that beautiful introduction. I must say you and Edwin have been an inspiration to Bruce and me over the years, and it feels like we've known you for much longer than just 11 years. To all of you who are involved in the Astronomical League of the Philippines, I congratulate you for all of your efforts. And for those of you who came on a little early and saw that beautiful video, it's just remarkable all you've accomplished. So it's an honor for me to be here today to talk to you about one of my favorite subjects, galaxies. And as Imelda indicated, much of what I talk about that's my work today was done in collaboration with my favorite colleague, Bruce. So with that, let me begin the presentation. Astronomy, of course, is the oldest science, and for across the millennia, across the globe, it has inspired and united us as we all look at the same sky. It's hard to believe that it's only been 100 years since we've realized that there are other galaxies, and that required having telescopes big enough and techniques clever enough to figure that out. Here is just a montage of some of the many famous people who were involved in early discoveries about galaxies, starting with small ground-based telescopes to larger telescopes, using various techniques like spectroscopy. Finally, they realized and showed that there were other galaxies beyond our own.
Debbie, excuse, we're not seeing
Yes.
your slides.
Okay, let's see. So I wonder why this is. Let me, very sorry. Thank you.
No, sorry about interrupting there, but
No, I'm glad you
Here we
did. You would have
Yeah,
missed the whole
perfect.
show. Okay, let's see this. Let's try this again. Okay, it looked fine on my
Yeah.
screen. My apologies. Okay, so
Great, we can see it now.
we've got the inspiration of the universe, and so here in the montage are some of the early people working on realizing that there were other galaxies. So we now understand that there are something like 100 billion galaxies. So what is a galaxy? Galaxies are gravitationally bound collections of billions of stars and gas and dust. They come in lots of different masses and sizes and shapes, but in the local universe, that is what's around the Milky Way, three main types dominate. We've got elliptical galaxies, which are three-dimensional distributions of old stars. They don't have much gas available today, so they don't make new stars because they used it all up early on in their formation. Because the stars that remain are low mass stars, which are cool, elliptical galaxies appear red. In contrast, we have spiral galaxies, which are flattened shapes like giant pinwheels. They have a central bulge. They've got spiral arms, and the arms tend to be blue because new stars are forming there. And when we have a collection of stars forming, we've got low mass and high mass stars. The high mass stars are very hot, and so we're dominated by the blue light from these stars. And then there are regular galaxies, which are chaotic little systems, which have a lot of gas available for new star formation today, so they too appear blue. Spiral galaxies, like our Milky Way, can contain a wide range of numbers of stars. The Milky Way contains several hundred billion stars. And again, gas and dust, which are mixed together, out of which new stars form. So they're like a giant frisbee or a giant dinner plate where we have the central bulge, many spiral arms, but the details can vary. And sometimes there's an elongation called a bar, and we see the bright spiral arms where new stars are forming. Sometimes we see them from the side, so we get a good view of the bulge and the disk. Now, it's the rotation of these galaxies in the flattened disk that generates the spiral structure. And if a wave, a pressure wave, ripples through the disk, then it can sustain the spiral structure for a long time. Elliptical galaxies can contain anywhere from 1 billion to as many as 1 trillion stars. They all look very similar to one another. They don't have any structure. They're centrally condensed balls of stars. And so here we have different exposures, but it's basically stars all the way down. They don't have any ordered rotation. They've got stars going in orbits around the common center of mass in 3 dimensions. So that maintains their spherical shape. Irregular galaxies are much smaller than spiral and elliptical galaxies, typically 1/10 to 100th as massive. And they didn't use up their gas early on because they didn't achieve densities great enough for gas clouds to collapse to make stars. So that process is happening now. So when we look at different filters, we see lots of activity. If we're highlighting blue light, then we're seeing the hot young stars. As we look to the infrared, as in this middle image, we're using a filter that in the red and then going to the infrared wavelengths that highlights different kinds of activity. When we have high mass stars near gas clouds out of which they form, the gas is mixed with dust, and the hot stars excite the dust grains, and so they radiate. And in fact, we can strip in the red wavelengths, we can strip hydrogen electrons from the hydrogen atoms, and they recombine to produce a red light. So as we look to longer wavelengths, we can see the signposts of the star formation. In this composite image, we see some red regions here known as H2 regions, which are the ionized gas caused by the hot stars. So gas provides insights into the conditions in the early universe as we look at galaxies at different distances. So we'd like to understand how and when they first formed and how do they evolve. Unlike other sciences, astronomy relies on indirect evidence. So we have to look at the radiation that comes to us across the electromagnetic spectrum, or we can observe gravitational effects as galaxies move near one another, and that tells us something about their masses. So moving on from ground-based telescopes to look at a large number of very distant galaxies, we rely on telescopes above our atmosphere because they can extend from ultraviolet to infrared wavelengths, and ultraviolet wavelengths that don't get through our atmosphere and infrared wavelengths that also don't get through our atmosphere. So of course, we've had the Hubble Space Telescope since 1990, a wonderful telescope, still going strong. It's a relatively small mirror compared to ground-based telescopes, but being above the atmosphere is what makes all the difference. And we also had the Spitzer Infrared Telescope that was launched in 2003 and was decommissioned in 2017, far exceeding its lifetime as well. Of course, now we have the James Webb Space Telescope, far exceeding expectations. And in a few years, we'll have the Nancy Roman Space Telescope. Both of these are infrared telescopes designed to look at longer wavelengths than what Hubble can see. The Roman telescope, now under commissioning, is about the size of Hubble, but looks at longer wavelengths and also will have a field of view that's 100 times larger than what Hubble has. So together with all of these, we can study starlight and dust. Plus, we also have radio telescopes to study gas. Here we have two radio telescope arrays, the Atacama Large Millimeter Array in Chile, which is designed to look at millimeter wavelengths, so it can detect molecules like carbon monoxide, which is mixed in with the molecules in a giant gas cloud. And then we have the Very Large Array in the US, which is designed to look at centimeter wavelengths that can detect the electrons moving around in hydrogen atoms. 100 years ago, Edwin Hubble began to classify galaxies, and he was concentrating on the ellipticals and spirals. He put together what's now known as a tuning fork. So he's got ellipticals of various roundnesses compared to the spirals, and the spirals can either have a bar in the center or not a bar. And we now know that ellipticals, as I mentioned before, are not rotating. Spirals are rotating, and they rotate at different speeds depending on the mass of the central bulge. So the shapes of galaxies reflect their underlying physics, the conditions under which stars and gas are moving. And the colors reflect their star formation histories, as we'll explore later, because stars change color as they age. And when we look at galaxies, we're looking at composite starlight. This is a map of our galaxy that I helped National Geographic produce about 30 years ago. It still represents our galaxy reasonably well. Of course, it's difficult to determine the structure of our galaxy when we're sitting in it. We can look at gas clouds up close, we can look at stars up close, and so that's very important in understanding their overall distributions. But we really need to turn to other galaxies to interpret what we're seeing when we're sitting inside our disk. So we now realize that we have an elongation in our center that's a bar. It's a small bar. We're about halfway out in the disk right here, and we have a number of spiral arms. So if we look at a schematic of the components of the Milky Way, top view, we see the bar, we see the sun halfway out. We see a lot of star formation going on all over the galaxy, but primarily in spiral arms where the gas is most concentrated. From the side, we see a bulge that's old low mass stars. And we see a halo of stars in the form of globular clusters, which are collections of 100,000 stars. And these are the oldest components of our galaxy. And in fact, we think they came in from other galaxies, as I'll describe more a little bit later. And then we have the disk, and it's the disk where the gas and dust have been concentrated by gravity, and that's where the new stars form. Now, stars have different orbits in a galaxy depending on their location. So the stars in the halo all orbit the galactic center, but on their own orbits. And so they span a three-dimensional space. whereas stars that are forming in the disk are just following the galactic center in circular motion. As I mentioned, galaxies can be randomly inclined to our line of sight. And if we're doing essentially a flyover of a galaxy, we call that a face-on view, which helps us to understand the details of the spiral structure. But this edge-on view is of a galaxy of the same type as the one on the left. We're just seeing it from its side. And so that gives us information about how thick the disk is and how big the bulge is. Looking at another edge-on galaxy on the left, we can compare it to that band of light in the sky that we call the Milky Way, which is, of course, also the name for our whole galaxy. And what we're viewing with that band is just the plane or disk of our galaxy. We've got black running through the midplane because dust grains block starlight, so dust and gas are well mixed. And if we're just looking at optical wavelengths, that's what we see. We see the red H2 regions dotting the Milky Way too, because that's where new stars have recently formed. Now we see stars are all around us in the sky because we're sitting in the disk, and the disk has some extent, and so we're looking at stars all around us. But the concentration here is the disk of our galaxy. If we zoom in on that and we use a radio telescope, we find that most of these black regions are filled with molecules. Most molecules are hydrogen. Hydrogen dominates in the whole universe. 90% of everything that's made of matter is hydrogen. But we've got a mixture of 100 other different kinds of molecules as well. I've already mentioned carbon monoxide, which is the second most abundant molecule besides hydrogen. And it's very easy to detect at millimeter wavelengths. And then we have the dust running through. Here's a big H2 region where we've got new star formation going on. If we look at one particular cloud, we see what's called the jewel box here. The cloud once extended all the way around here. Now we've got just this part of the cloud left over because this beautiful little cluster of stars used up all the gas around it and cleared out the remainder. And so we see a star cluster that formed out of a bigger cloud. If we go on more dramatic scales, we see the famous pillars of creation, the Eagle Nebula in M16, and we see three main molecular clouds. When we have a cloud that's this extended, we don't get star formation all at once. Typically, we have a pressure that pushes on the cloud from one end, and we have star formation that can eat its way through the cloud. So we have star formation just starting to form up here, for example. And we've got nebulosity all around the clouds because we've got the external stars that are interacting with the gases. This is a side-by-side view of Hubble and Webb, and so we see the dramatic difference as we're looking at the nebulosity surrounding the Eagle Nebula in the optical. We're dominated by these nebulous features, but if we look in the infrared, we peer through those features and we see all the background stars. We also see a clear separation between the top and bottom parts of this cloud, which is not as apparent in the optical. And all these dark regions in the optical are where we have dust grains that are emitting in the infrared. This dramatic star-forming region is actually just a small piece of a much larger region in our galaxy. So it's again by looking at these large-scale star-forming regions across our galaxy that we can then turn to other galaxies and try to piece together the picture of how stars form and evolve and how galaxy structure changes over time. And that means looking at very distant galaxies to compare them to nearby galaxies. Here's another view of a star-forming region, top and bottom, Hubble and Webb, and we see a beautiful detailed structure like waves sloshing around as these clouds are collapsing to create new stars. When we look at a star or gas or dust, it's helpful to use spectroscopy because spectroscopy gives us the chemical fingerprints that show us what these regions are made of. And so each atom or molecule emits at particular wavelengths. And so if we disperse the light with a spectrum, we can tell the composition. So here's one of the H2 regions up close, one of these ionized regions around hot young stars. And if we look at the spectrum, it's color-coded. We see the green is molecular hydrogen. We've got neon because we've got a mixture of some heavy elements too. The purplish region here is silicates, which are dust grains. Dust grains could be aluminum or magnesium silicate typically, or they might have some carbon. They might have some ices around them. And the red regions here are PAHs, polycyclic aromatic hydrocarbons, which, as the name implies, are just things like benzene rings, mixtures of carbon and hydrogen in ring-like structures that emitted infrared wavelengths. When stars form in clouds, they generally form in clusters. And on the left, we have part of the Pleiades, which is a collection of 1,000 stars. We can tell that the stars in the Pleiades and in other young open clusters like this are becoming unbound over time. Although they formed at the same time in a gas cloud that collapsed, the stars are dispersing. And so this cluster, the stars will drift apart over time. And that's what happened to our sun. We now believe that our sun formed in a small open cluster, which has since dispersed. So it looks like we're isolated, but we used to have neighbors. In contrast, we have old globular clusters that are the ones in the halo of our galaxy that I mentioned before, and they're three-dimensional distributions of 100,000 stars. They have so much mass that they stay together as these little round balls throughout their lifetimes. And because they're upwards of 10 billion years old, the high mass stars, which live a short time, are all gone now, and we're just left with the old low mass stars that stay bound together through life. So as we look at other galaxies, we need to understand what stars are doing, because in general, beyond our local group of galaxies, we're not seeing individual stars. We're seeing composite light from billions of stars, and the stars have different types, and the stars evolve differently depending on their type. So to figure out what galaxy light is, we need to know the color and brightness of a particular star as a function of its age and mass, the lifetime of a star of a given mass, and the relative proportions of stars of different masses. And we can tell all of this by studying stars in our own galaxy. And then if we look at another galaxy, if we look at a particular region, it has a color and it has a brightness, and we can make models knowing how stars evolve and how their colors change with time. And we can therefore determine the age and mass of a distant galaxy. So let's look at the properties of individual stars. We know that their colors depend inversely on their surface temperatures. All stars are 10 million degrees in the core. They're fusing hydrogen into helium. That's what makes them stars. But their surface temperature depends on the mass with which they formed and the stage of their evolution. So if we just plot the brightness as a function of wavelength, then we find that hotter stars are cooler than bluer stars. Here we have a star with a surface temperature of 8,000 degrees that peaks in the bluish yellow part of the spectrum. And here, if we go to 3,500 degrees, we have a star that peaks at about 6,000 or 7,000 angstroms, and that's in the red part of the spectrum. Our sun is yellow because its surface temperature is 6,000 degrees. And the relationship is that the peak wavelength of emission, represented by lambda here, in angstroms, is a constant over the temperature. So 3 times 10 to the 7th, the constant over 6,000 degrees would give us a peak at 5,000 angstroms, which is yellow light. So that's why the sun is yellow. As we look at stars in the sky, we can see these colors. If we have a nice dark sky, looking towards Orion, we have Betelgeuse, which appears very red, and Rigel, which appears very blue. And that's because, although they're both supergiants, they have very different surface temperatures. Betelgeuse is 3,000 degrees and Rigel is 30,000 degrees. We can also take spectra of stars to determine their composition and their temperature. We know that stars are all about the same to first order. They're 90% hydrogen, 9% helium, and 1% of heavier elements. That 1% at the very low level is very important because it tells us something about the gas cloud out of which stars form. Initially, there aren't heavy elements. We've got hydrogen and helium. And as high mass stars evolve, they eventually nucleosynthesize up to heavy elements. And in a supernova explosion, spew those heavier elements out into the surrounding interstellar medium. And so we have clouds that are enriched from these high mass stars that go on to make new stars. So later generations of stars will have a higher proportion of heavier elements than stars that formed in the very early universe. So we can look at a spectrum and see these details. And so this is a typical view of a spectrum, just as a rainbow. We've got absorption lines in stars because they have nucleosynthesis going on in the core. photons are generated from that transformation, and the photons work their way through the surface of the star, which is much cooler than the core. And so those cool gases in the outer layers are absorbing the photons. So that's why we see some dark lines. If we do a scan of the spectrum, then we can see some dips representing the absorption lines. So some of them are marked. Here's a hydrogen line and a sodium line, even an iron line. And so we can tell those details by a high resolution spectrum. But also we can tell the temperature of a star by looking at how strong certain lines are. Given that all stars have about the same composition, the hydrogen lines stand out more or less, shown up here, according to the temperature of the star. It turns out 10,000 degrees is optimum temperature for an electron to make a certain transition in hydrogen from one energy level to the next. And if the star is cooler or hotter, then those transitions are not as likely. So even though the hydrogen is present in all stars, these different strengths reflect the temperatures of the stars. Now, the brightness of a star depends on its size and temperature. So luminosity is what we use as the physical definition of the output of a star, and that's the amount of energy per unit time. So it depends on how big the star is and what its temperature is. So let's look at sizes. Here's the sun. A little middle-sized stars. They're much tinier stars, but sun's sort of mid-range. And then if you follow the arc to Arcturus from the Big Dipper star handles, you'll find this very large star, and look how much larger it is than the sun. And yet Arcturus is tiny, shown here, compared to, say, Betelgeuse. And so we have giant stars and supergiant stars and stars that are not so big. And we need to take all of this into account because stars will grow to different sizes over their lifetimes, and this affects their energy output. So if we're looking at composite starlight, we need to understand how all this goes. Here's a plot of the Hertzsprung-Russell diagram developed by two astronomers in the 1900s. We plot the star luminosity as a function of the star temperature. And it turns out we now understand that stars occupy one spot on what's called the main sequence throughout 90% of their lifetime. And that's where they're fusing hydrogen into helium in the core. After that, the internal conditions change and the star will eventually expand and cool. And as a hot gas expands, it gets cooler, and therefore we end up having a redder star, even if it started off blue. And so this is a different surface temperature that gives us our different color. So we have much more luminosity from a red supergiant than we do from a red star still on the main sequence. And so we need to understand the relative proportions of stars, and also understand that for a collection of stars at a different age, we're going to see very different colors and brightnesses for that region. So stars can have masses anywhere from 1/10 to 100th of a solar mass. How long they live depends on that mass. Higher mass stars fuse their hydrogen more quickly. And so the lifetime when they're fusing hydrogen and helium in the core is 10 to the 10th years times the mass to luminosity ratio. Excuse me. And so here we have an evolution off the main sequence over a period of time. So if we're looking at a cluster of stars that's quite old, all of the hot blue stars are gone. And so it appears very red. It's important also to use different filters to highlight these different emissions. If we just take a composite color image, we don't know the relative amounts of light. But if we use filters at the telescope, then we can sort out how much radiation we're getting at X-ray regions. Those are high energy events associated with supernovae. If we're looking in the ultraviolet, we get emission from the hot young stars. So these are stars that are 10 to 30 times the mass of our sun typically, and so they dominate in the ultraviolet. And these are the young stars that only live a few million years. If we're looking in the optical wavelengths, here are two different stretches of the same image, so we can see the central structure, and it's saturated here. This is looking at stars that are a few times the mass of the sun, and they live about 1 billion years. So as we go from short wavelengths to longer wavelengths, we're looking at older stars. As we go to 3.6 microns, 36,000 angstroms, so beyond what our eye can see, we're looking at light dominated by stars that are 1/10 the mass of the sun, that live for billions of years. And yet in all of these, we're seeing spiral structure, and that gives us clues to how the spiral structure formed. As we go to even longer wavelengths, 8 microns and 24 microns, we're looking primarily at the dust that's been irradiated by the hot stars nearby. And even longer wavelengths, 21 centimeters, here we're looking at the atomic gas distribution. So it's important to look across the electromagnetic spectrum to figure out what relative contributions we're getting from the different stars and what their structures look like. Here's a view of the center of a galaxy with Hubble on the left and with Webb on the right. And these are the identical regions, but we're highlighting very different kinds of activities. So we see the nice spiral arms in both cases, but look at all the dramatic filamentary structure that appears when we're looking in the infrared with Webb and highlighting the dust structure. So the dust and gas are mixed together. That's what makes the new stars. But we really highlight what's going on with the gas and dust clouds in the infrared. So look at this big hole here. You see there's sort of a circular region here, but you don't think of it as a hole. And in fact, all of these holes are regions where supernovae, high mass stars, have exploded and cleared out the regions around them. And yet we still see this overall spiral structure. And in the middle, we see a composite image of Hubble and Webb, optical through infrared. Here are some more recent images of a couple of galaxies in Webb, just showing the very intricate dust structure that we get in these galaxies. Now, when we're looking at very distant galaxies, we have to take into account the fact that the universe is expanding, and that means that light from distant galaxies is redshifted. The light is actually stretched by the expansion of the universe. This was realized 100 years ago when Hubble and Humason and Lemaitre were plotting the velocities of galaxies as a function of their distance, and they found that more distant galaxies were moving faster away from us. This would be true no matter what galaxy we're standing on in the universe. As the universe is expanding, all galaxies are moving away from all other galaxies. So as we're looking at a spectrum of a galaxy, these absorption lines are in the lab for comparison with other objects. Here we have a relatively nearby star, and we see that the lines are shifted a little bit to longer or redder wavelengths. If we look at nearby galaxies, we see a bigger shift. And as we go to more and more distant galaxies, we see a much bigger shift. And so the shift of those lines is actually giving us the velocities of the galaxies. This is known as the Doppler shift, which you're familiar with if you've ever heard a car go past you blaring its horn. So here on the right, we have a fire truck. It's moving towards a person. And you may have noticed that if the horn is on, it appears to be very high pitched as it's coming towards us and lower pitched as it's going away. Sound might behave the same in this regard. We can think of them as waves. And so if we're looking at an object and it's emitting, imagine that the light is coming off as concentric circles whose separation of the wave fronts represents the wavelength of light. If the object is moving towards us, the wave fronts get bunched up. So there's shorter wavelength, and shorter wavelengths corresponds to a blue light. And if the object is moving away, then the wave fronts get further and further apart, and so the light appears to be stretched to longer wavelengths. Now, for objects in our galaxy, we have a relationship between the shift in the wavelength. Delta lambda is the difference between what was observed and what was emitted, compared to what was emitted by the object. And that's given by the velocity of motion towards or away from the object, compared to the speed of light c. There's a relativistic correction when we're looking at high velocities. But basically, from these shifted spectra, we could figure out the velocities of objects. And therefore, using a plot like this, figure out to first order how far away they are. So this term, the redshift, is defined in terms of the relative shifted wavelength. We have this relationship, the observed wavelength compared to the wavelength that was emitted is equal to z plus 1. So what does that mean? If we're looking at a galaxy at redshift 4, suppose it emits an ultraviolet at 1500 angstroms, then 4 plus 1 is 5 times 1500 is 7500 angstroms. So what was emitted by the galaxy in the ultraviolet would appear as far red light to us. So we need to use a red filter to look at the same emission in this distant galaxy as we would for an ultraviolet filter in a nearby galaxy. So it's important to use different filters, and also to keep in mind that we need to account for the redshift of a galaxy in order to interpret what we're looking at. Well, what's really cool about astronomy, even though we can only look at things remotely, is that we've got a time machine. As we look out in space, we're looking back in time because light has a finite travel speed. Light travels 6 trillion miles in a year. That's 1 light year, so that's a distance. Our sun, 93 million miles away, gives us its light today as it appeared 8 minutes ago when it left the sun. Jupiter, on average, is about 4 times further away, so its light takes about a half hour to reach us. Our nearest star, Proxima Centauri, is 4.25 light years away, so we're seeing it today as it was 4 years ago. If we're looking at our galaxy, it's about 100,000 light years across. And so as we look at different regions of our galaxy, we're looking at starlight from thousands of years ago getting to us today. Galaxies tend to be clustered, and the Virgo cluster is our nearest cluster of galaxies, and yet it's 65 million light years away. So the light we see today was emitted when dinosaurs were still walking the Earth. We have a model for the expansion of the universe, so we can plot what it means to talk about a different redshift in terms of the age of the universe that we're sampling. So as we go to more and more distant objects, we're getting baby pictures of them, even though they have evolved. And that's what allows us to put together a picture of how galaxies evolve. We can look at them a long time ago if they're very distant, and we can look at galaxies near us today, and we can see how they change on average. So here's a plot of the age of the universe. Here's today, 13.8 billion years old. And if we go out to a redshift 4 object, we're looking at it when the universe was less than 2 billion years old. If we look at redshift 2, we're looking at it when the universe was about a third its current age. And redshift 1, when the universe was about half its age. So in 1996, Hubble looked at a blank piece of the sky in the northern and southern hemispheres for many, many exposures, regions where there were no known stars or galaxies, and yet thousands of galaxies were revealed in these blank regions. When a new camera was put on a few years later, this was the first light image of a beautiful galaxy. And I was intrigued by this pretty galaxy, but particularly by the little things in the picture. So I liked these little galaxies down here, which look like nothing I had ever seen in the nearby universe. They appear to be like an edge-on disk, except there's no bulge, and there are these huge knots of star formation. And it turns out they're all over the sky as you look at very distant objects. Now, the Hubble Ultra Deep Field was imaged over several years with different filters, and it reached to distances on average twice as far as the Hubble Deep Fields. And now we can even see galaxies out to redshift 11. So this background for my whole slideshow is the Ultra Deep Field. To give you an appreciation for what it's looking at, which required 400 orbits of Hubble time, if you hold a needle up at arm's length and look through the hole, that's the relative piece of the sky you're seeing compared to the whole sky. So it's a very, 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 very tiny piece of the sky, and yet there are 10,000 galaxies in that image. If we look at part of the ultra deep field, we can see that there are some ellipticals and some spirals, but a lot of things that don't look quite right compared to today's galaxies. The young galaxies, on the whole, are clumpier than today's galaxies. As we look nearby, seeing ellipticals and spirals, go a little bit further away, we still see ellipticals and spirals. But then when the universe was only half its current age, they start to look distinctly different. In fact, they're only about half size when the universe was about half its age because they grow over time, but also they lose their spiral shapes. So Bruce and I looked at the 1,000 galaxies in the ultra deep field, which were large enough, resolved enough for us to be able to see structure. And so out of those 10,000, 1,000 of them were big enough. And so we've got the clumpy galaxies are the 4 kinds at the top, and then we've got spirals and ellipticals. So the clumpy galaxies come in different kinds. We've got the chain galaxies, which have these knots of star formation in a string. The clump clusters, which have the knots, but it looks like we're viewing a galaxy that's a disk galaxy from the side for the chain and from the top for the clump cluster. And then we've got doubles and we've got tadpoles, which have a big head and a little tail behind them. So these are things that are very unusual compared to nearby galaxies. Elliptical and spiral, ellipticals we see, as far as we can see galaxies, we see ellipticals, but spirals disappear by and large after a certain point. So we wanted to look at the statistics of these different galaxies as a function of their redshift. And we find that beyond redshift 2, we simply don't have many spiral galaxies. So we've got spiral galaxies like ours first appeared when the universe was about a third its current age. And so we have different spirals. They look sort of like today's spirals, not quite in detail. The arms are a little more chaotic and the star-forming regions are a little puffier, but they are recognizable as spirals. And so redshift 2, this is significant because it says that the disk have started to settle down. In the early universe, everything was very turbulent, and we can now measure gas motions in galaxies at redshift 2 and find out that the gas motions are 100 kilometers per second in a galaxy, whereas in nearby galaxies today, they're moving at about 10 kilometers per second. And that difference allows spirals to propagate in a disk. And so this is telling us about changing conditions. Here's a galaxy that's interesting, even though it's at high redshift, or closer than redshift 2, but still distant compared to our local galaxies. You can see in the infrared this bar-like structure and a beautiful two-arm structure. So conditions are right to form spirals at this time. Today's spirals have a lot of star formation in the arms, and we can see that in the optical, but if we go to the infrared, and here's two sets of galaxies, optical and infrared, we see that there are knots of star formation that really stand out in the infrared images. These are very large-scale regions, a few hundred light years across, but they contain 100,000 stars. So very large regions of star formation. Here's another galaxy, again in the infrared on the left and the optical on the right. And in the dust lane, it looks black, but in the infrared, we see these knots of star formation. So what's going on is that we've got gravitational instabilities that cause gas clouds to collapse. That is, they've got enough mass that their own gravity pulls in the regions. And so you have to go a certain distance away before you have enough mass for another collapse. And that's why these beads tend to be rather evenly spaced in a spiral arm. Here's another galaxy where we're looking at the infrared and optical. And again, you can see these little knots of star formation beading the spiral arms. But if we go to galaxies that are further away, then we find that by redshift 2, these massive star-forming regions are much more massive than in local galaxies. These complexes or clumps contain 10 million stars. And that's because the gas is more turbulent, so you need more mass to overcome the random motions in the disk. If we go even further to the clumpy galaxies, when we've lost the spirals, we see that the complexes contain 100 million stars. And so these are very massive star-forming regions in otherwise tiny galaxies. So we've got a simulation here showing a series of time steps here to here to here to here, looking at top view of a clumpy galaxy where the black and yellow show where we have these giant clumps, and just let the galaxy spin. And the clumps are so massive that they interact with each other and get dragged to the center to build up a bulge. Or sometimes they disperse to help build up the disk. And the time scale here is about 1 billion years. So here we see a side view of the same object. Here are the clumps. And over time, those clumps are going to build up a bulge. So this is what looks like a side view of a spiral galaxy. So again, on 1 billion-year time scale, any particular galaxy will evolve from a clumpy galaxy to a spiral galaxy. So here's our proposed evolutionary sequence. Clumpy galaxy starts to get a little hint of a spiral structure with massive clumps, and eventually the clumps are less massive and the bulge starts to build up and we get a spiral galaxy. So the transition is, we've got gas that's dripping in from around galaxies, as I'll describe more later. And this helps build up the size of a galaxy, and it causes stars to form. And as we get more and more stars, they drag down the disk, which is kind of fat initially, like in regular galaxies. They drag it down into a thinner disk. And we radiate a lot of that energy away, and therefore we've got a less turbulent disk to form new stars that are less massive in their complexes than long ago. Galaxies often have neighbors that affect their evolution. So here's Stephan's quintet with Hubble and Webb. When you have galaxies interacting, if you have large galaxies interacting, they are going to merge to create an elliptical galaxy, regardless of what they were initially. So here we have a bunch of spiral galaxies. These two are already merging. And in Webb, we can see massive star formation between the galaxies. But eventually, all these are going to make one big elliptical, because you can't take disk galaxies and turn them into another spiral galaxy. They're randomly oriented. They've got collisions going on. So they end up as a three-dimensional ball. So ellipticals will merge to make bigger ellipticals. Spirals will merge to make ellipticals. Spirals and ellipticals will merge to make ellipticals. This is a picture of the same region that was imaged with China's FAST radio telescope, and it's color-coded so that red shows the atomic hydrogen gas. So the gas is mostly confined to galaxies, except for a little bit that exists all throughout the universe. But it turns out these galaxies, as they interact, have pulled out gas from each other that creates a big halo around them. We can look at pairs of galaxies interacting too, the famous M51 with its little companion. And as the companion is going around, it's pulling material. And so we've got a long tidal arm. A tidal arm is just when we have a differential gravity. You know, the gravity is weaker as an object gets further away by the inverse square of the distance. And so if we have a galaxy, one side of it is pulling more strongly to the other object, and the backside has lesser gravity. So you end up pulling out tidal features, just like the moon and sun pull out the tides on Earth. If we take a very deep exposure in the optical of this image, even though most of the light is confined to the spiral structure, we do see stars far out too. And that's a result of this interaction of the two galaxies pulling out stars from each other. Now, here's the first simulation of interactions. And so we've got the Tomb Rays did this model in 1970, two disk galaxies represented by these dots for stars. And as they move nearer and nearer each other, they begin to pull out these tidal arms. And so this is trying to match what we call the antennae, two pairs of galaxies that are merging in the center. And if we blow up that central region, this is a Hubble view of the massive star formation going on caused by the violent interaction. And this black region here where the dust is blocking starlight appears in emission with an infrared telescope. The same pair of galaxies I showed before, we've got in the optical with Hubble and in the infrared with Spitzer, and we're looking at carbon monoxide molecules using ALMA. And so we see this nice spiral structure in different elements. And it turns out that with a radio telescope, we can measure the velocities. And so we can do a computer simulation of the interaction. And here's how it goes. Right about now is what the galaxies look like. But after about 1 billion years, they are going to emerge to create an elliptical galaxy. Andromeda is our nearest big galaxy, about 2.5 million light years away. It's a little more massive than the Milky Way, and we're on a collision course. We're going to merge with Andromeda in 3 or 4 billion years. So here's a dramatic simulation of the merger sequence. Here's our Milky Way disk. Here's Andromeda getting closer and closer until it gets close enough that it triggers violent star formation in the gas clouds in the galaxies. And here we see that, and eventually the centers are going to merge, and we're going to live in an elliptical galaxy. So this is in 3 or 4 billion years. So the sun will still be around then. Of course, it will have expanded past red giant, so Earth probably won't be around. It'll be swallowed. But if we lived in an elliptical galaxy now, we probably wouldn't know much about astronomy because our light would be dominated by all the nearby stars. The large and small Magellanic Clouds are nearby irregular galaxies that appear as permanent clouds in the southern hemisphere. They're about 55 kiloparsecs, or about 150,000 light years away. And so here they are in close-up. We're ripping them apart. So because we're a big galaxy and they're tiny, we're not going to merge with them and make an elliptical. We're just going to shred them. So we see this happening already. Here's in pink the gas tail that's being pulled out from the gas in these galaxies as they orbit. And as we look in the sky, it turns out we see lots of streams, both in gas and in stars, particular orbits as a particular galaxy gets ripped apart. So it looks like we have consumed about 24 galaxies. in our halo. And here's a simulation of a little galaxy coming near a big galaxy. And you can see it just being shredded apart. Some of the stars will merge with the disk, but early on in the stages, we see all these star streams or gas streams in the sky. And in fact, with the Sloan Digital Sky Survey, we see many, many star streams. Here's different names for different streams, all of which came from distinct galaxies initially that we ripped apart. And we can blow up a region in this stream and we see some globular clusters. Well, if we look at distant regions, we can see in the Hubble frontier fields imaged a few years ago, clusters of galaxies, and we can see what they look like compared to clusters today. And this is going out to redshifts 1 to 2. And so we see some chaotic looking galaxies and some that are starting to look like normal ellipticals. Sometimes we can see really tiny galaxies that we call little blue dots, for want of a better name. It's very descriptive. Bruce and I thought these little blue dots might be the centers, the very active, high emission centers of extended galaxies. But it turns out when we stack the images of these galaxies, that's all that it was, just little blue dots all the way down. And we measured their masses. And in fact, we believe that they are the present day globular clusters that we see in galaxies. They have about the right mass to have been globular clusters forming long ago. And then as they come near a galaxy like ours, they just get subsumed into the halos. Galaxy merging happens quite frequently in the early universe. And here's a simulation of little galaxies growing into bigger galaxies through the merger. And now we have Webb showing some distant galaxy clusters, and we see evidence of merging already happening there with these tiny galaxies. As we look across our universe, we see distributions of clusters of galaxies. So these are known as superclusters. And so they fill the sky, not uniformly, but we see a uniform distribution repeated on big scales. That is, we see these big arcs and rings everywhere throughout the universe that are clusters of galaxies. This was a map made in the 1970s showing the distribution of then known 1 million galaxies. And this image always looks to me like a large bubble bath where you take a slice. You see the galaxies everywhere repeating the overall structure, but not uniformly filling the space. There are what appear to be big bubbles if you took a slice through, and these bubbles are 100 megaparsecs, or about 300 million light years across. And these bubbles reflect conditions in the very early universe that first allowed clumps to appear. That is, when we first started to make atoms and how they were beginning to clump together. So we've got cosmological simulations showing gas in the early universe, just hydrogen, randomly distributed throughout the universe, but a little more in some places than others. And so where there was more in some places than others, there was stronger gravity. And so clumps attracted more clumps. And ultimately, you get galaxies forming in these orange regions where the gas has collected to a sufficient density. Well, it turns out that it's not just ordinary matter like hydrogen that we have in the early universe. We have dark matter too, which we know very little about. We know it exists because it has mass. It doesn't interact with photons, so we can't see it, but we can see the effects of it in the rotations of individual galaxies and in the motions of galaxies in clusters, where we can measure the starlight and the gas, and we know there's more mass than that. So we think that all galaxies are surrounded by dark matter halos. So here's to scale a dark matter halo around what we would call a disk galaxy. So in the very early universe, it's the dark matter that starts to clump first, and then it attracts normal matter. So we've got computer simulations that show this development of structure, starting with now the dark matter. Here's redshift 2, and these cosmic filaments starting to get denser. And ultimately today, we've got clusters of galaxies that have formed. So in these simulations, you get information like temperatures and velocities, and you can zoom in and look at real galaxies formed in the simulation. So the trick is to look at galaxies at great distances and nearby, and to figure out what structures formed when. Like we think that the majority of spirals started forming at redshift 2. We've got clumpy galaxies as we go further away. Does that match the simulations? And if not, the simulations need to be tweaked. So the simulations do a very good job on a big scale. The details on the small scale are not quite right yet in terms of when you get certain types of galaxies and exactly what they look like. But there are remarkable simulations going on. Now let's take this simulation where we've got 320 kiloparsecs, so that's 1,000 times 1,000, that's 1,000,000 light years across. So there's a big box with a cosmic filament, and let's zoom in on this part. And now this is the size of a galaxy, right? A very tiny spot in the center, size of a galaxy. And so we can look at these galaxies forming in the simulation. This is a redshift 2 simulation. And top view of one region shows what looks like a clump cluster, a clumpy galaxy. Side view, we'd call it a chain galaxy. So we're reproducing the clumpy galaxies at the right redshift compared to observations. Well, it turns out that there are some nearby tiny galaxies, much less massive than the clumpy galaxies that we're looking at high redshift. And because they're so low mass, they haven't evolved much, because all actions in a galaxy are driven by gravity. And if there's not much mass, there's not as much gravity. So star formation takes place more slowly. So these are actually tadpole galaxies, like what we see at high redshift, but much tinier. So we see massive star formation going on in one part of the disk. And we've got Hubble observations of these. And here's one where we've got new star formation going on. We see the H2 region. We can take a spectrum and find out that this is relatively metal pure gas. And so this means that this is not star formation that happens in this disk, because high mass stars form gas clouds that form new stars that are enriched with heavy elements. This is gas that dripped in from the cosmic web and triggered star formation. And so we believe that these are the low mass local analogs of some of the clumpy galaxies that we see at high redshift. So with Hubble, we're looking at normal galaxies nearby. With the Hubble deep fields, we go to when the universe was half its age. With the frontier fields and the Hubble ultra deep fields, we're pushing to within 1 billion years after the universe began. With the Webb, we're pushing to within less than 500 million years after the universe began. So we're probing the very first stars and galaxies. So we've got a distant galaxy cluster from Webb. Look, and these are both in the infrared, near infrared and longer wavelength infrared. And we see galaxies that would otherwise not appear to us. So this is a cluster that's already forming in the very early universe. Webb has found 4 very distant galaxies. Here's a Hubble image of these galaxies, and Webb going to longer wavelengths and also having a mirror that's 3 times larger than Hubble shows the details. And this is a spiral galaxy. You can almost see it here, but it's quite clearly a spiral galaxy in here and here when you're looking with Webb. So you only really know the distance of a distant galaxy if you can take a spectrum and get a precise measurement of a shift of a particular line that has been emitted, like a particular hydrogen line or oxygen line. So here's a galaxy at high redshift, and here it is in different filters. And with spectroscopy, it's been determined that this galaxy is actually at a redshift of 9, which corresponds to just 500 million years after the Big Bang. And the surprise is that it's a billion times the mass of the sun. Now, 1 billion solar masses is a small galaxy compared to galaxies in today's universe. But in the very early universe, again, looking at simulations, no one expected a 1 billion solar mass galaxy just 500 million years after the Big Bang. And this means that the simulations need to be tweaked to get some massive galaxies earlier on, some particularly dense pockets where some big galaxies could grow. We know there are not a lot of massive galaxies at high redshift, but the fact that there are any means that we don't have the models quite right yet. Now, here are 6 massive galaxies that were formed just 500 to 700 million years after the Big Bang. So all of these red dots are those galaxies. And here we have one that's a candidate for being at a redshift corresponding to just 236 million years after the Big Bang. So we're pushing the boundaries. We understand galaxies locally, and with Hubble, we're all the way out to redshift 11 now. With Webb, we're out to redshift 16. So we're exploring when the very first formation of stars and galaxies appeared, and we're putting together this great cosmological evolution for galaxies. So just remember, as we're exploring the sky with different countries, with different instruments, with different engagements, we're all together under that same sky. So thank you.
Thank you so much, Deborah. So much information. I think I have to go through your lecture again, so I'll be able to really understand and comprehend what you've told us. But like I said, we do have a lot of interested attendees, and your lecture triggered a lot of questions, and I hope we'll be able to answer them.
Great.
So I'm gonna start to read some of them. Wait. So here I'll read them from the first ones that were asked, and this is one of the first questions. It's regarding galactic structure. What is behind the formation of galactic structures? Do they have the ability to change over time? It's from Ren.
Yes, thanks, it's Ren.
Yes,
Yes,
yeah.
so yes, indeed, that's what we see. The galaxies have different shapes and different masses, and so they do evolve over time. So we think that in the early universe, we basically have the really dense little clumps will form elliptical galaxies. Those stay as elliptical throughout their lifetime. But as we've seen, the galaxies that are a little lower mass initially can form a disk just because they are spinning, and that spinning causes the disk to shrink down. And so we have a galaxy that's dominated by a two-dimensional structure. And it's that structure which is a clumpy galaxy initially, but it's very turbulent. And so the random motions are almost as large as the spinning of the galaxy. And over time, through radiation, that turbulent gas settles down into a more quiescent state. And that's when we can start to get the spirals. So we believe the ellipticals are ellipticals throughout their lifetime, and they can be big or small. They can grow if we have galaxies merging with them. They'll grow to be bigger elliptical galaxies. We think that on average, galaxies were about half their size when the universe was about half its age. But it's the clumpy galaxies that are interesting in terms of the Milky Way, because the Milky Way would have been a clumpy galaxy early on, and it became a spiral galaxy when the disk finally settled down and a spiral structure could be generated.
Oh, thank you. And this is a related question, although it came at a later down the line of questions. And this is from Yobel Lee de la Cruz. What causes the central bulge in a galaxy? What conditions cause galaxies to form their respective shapes and change over time? How do the presence and characteristics of a central bar affect the dynamics and evolution of a spiral galaxy? And she also said, may we please have a copy of your PowerPoint presentation?
So I think the lecture will be the recording will be made available, right? Yeah.
Yep.
So at some point everyone can see this. Yes.
Yeah. Thank you.
Yes.
So she had several questions here. Yeah.
Okay. So that's a lot of questions. Let's try to unpack them. So how does the bulge form? We're not sure. Based on the work that Bruce and I have done with simulations, we think that one mechanism that forms the bulge is that you've got these giant clumps that randomly form in a disk of gas, and these clumps can merge together by gravity. So our simulations show that you can get a buildup of a bulge that way. Now, some people think that, and so this is related to black holes, and I'm not going to go there except to say that it appears that most galaxies have black holes at their centers. And the question is, do you start with a big black hole and build up a galaxy around it, or does a black hole develop as the galaxy is developing? And so these we don't understand bulge formation fully, but we do have simulations that suggest that you start with a disk and then you build up a bulge from the interactions of massive clumps that can all coagulate to the center. In terms of the bar structures, didn't have time to explain details about spiral structure formation. Spirals are rotating disks that have a wave that can ripple through them, and you can have a spiral structure that lasts a long time or a short time. Most galaxies that we see that are spirals, like the Milky Way, have essentially a standing wave, which is a wave sloshing back and forth in the disk. Now, how is that wave generated? It's like when you're on a swing, pumping your legs to make the swing go, and you have to figure out exactly how to pump your legs compared to the length of the string in order to develop a standing wave that's your swing. Same thing in a galaxy. Another galaxy can swing by and trigger a wave. And unless the wave is at the right frequency, then the wave just passes by. But if it's in sync with the rotation of the galaxy, that can generate a standing wave. So you can have a galaxy companion triggering a spiral wave that gives long-lasting spiral structure. On the other hand, simulations show that you can also take a bar. Now, a bar is just an instability that automatically happens in about half of galaxies. In computer simulations, randomly, as you've got a spinning disk with stars, sometimes you're going to make a bar structure. And it turns out that bar structure can generate a standing wave too, just like take a stick and turn it in water. So that bar acts as a driver of the wave from the inside. Let's see, now I forgot another. So yes, we can have a lot of evolution of galaxies over time. We don't understand bulge formation fully, but we're starting to have hints about that.
Yeah, I guess you address all the questions she asked.
Okay.
And the next one is from Michael Cruz. Is the distribution of the galaxies within the observable universe uniform in all directions? Or is there a particular area that galaxies did not occupy?
Yeah, great questions. And so this goes back to the large bubble bath picture we have of the distribution of galaxies in the universe, that in fact, they appear to be concentrated on the surfaces of bubbles, intersecting bubbles in the universe. And there are galaxies throughout the universe, but they're not uniformly distributed throughout the universe. We have on these bubbles a higher concentration, and these correspond to cosmic webs coming in. We've got this filamentary structure. And so where we have the filaments overlapping, we're going to have more matter. And so we're going to have galaxies that can build up there more so than in the regions between the filaments. And so we have the bubble structure repeated throughout the universe in the same way everywhere. But we do have regions that have more galaxies and regions that have less galaxies, because it's the Swiss cheese collection of gas initially.
Okay, thank you. And this is from Thomas Encarnacion. At what speed is the universe expanding? Will there come a time that an object at the edge of the visible space will become invisible to us as it falls into space beyond our visible horizon?
Right. So this is a great question. And it was why Hubble was originally launched, to figure out exactly what the expansion of the universe was. Because at the time Hubble was launched, people thought it was one of two values. Maybe it's 50 kilometers per second per megaparsec, or maybe it's 100 kilometers per second per megaparsec. And if you trace back the first order expansion of the universe, you get the age of the universe. And so this meant, depending on which model you believe, the universe was either 20 million years old, or 20 billion years old, or 10 billion years old. And so Hubble was launched and looking at various nearby objects and bootstrapping our way to more distant objects. And now the value from many different observations seems to be almost dead in the middle, somewhere around 73 to 75 kilometers per second per megaparsec. So that's what we think is the expansion rate of the universe, but it's changed over time. Right now, the universe is accelerating. And so, yes, your question about objects slipping away from our field of view, that's true. We don't see the whole universe because some of it has gone beyond the light travel time. And so, yeah, we're only seeing a fraction of the whole universe now.
Thank you. And this is from Jay Soreliano. I have seen an art, and I think you touched on this, Deborah. I have seen an article which contains information about a billion years from now, the Milky Way and Andromeda will merge and will be called Milkomedia. Now the scientists have expanded their knowledge and until now continuing various studies related about the field, my question is that that occurrence has a higher chance to happen in the near future? I guess he was referring to the merging
Right.
of the galaxy. Yeah.
Milkomedia, I love that. I haven't heard that name for the merger. Yeah, we do believe that we can tell these motions primarily now from Gaia with the satellite, where we're mapping out 1 billion stars and mapping out their velocities. That's and looking over time how distributions of stars have changed in our galaxy at very, very, very tiny scales. And so, yes, we believe this merger will happen in 3 or 4 billion years. But
Okay.
it will happen. That's for sure.
Thank you. This is from John Lawrence Febrero. Yeah, Febrero. Were there any new findings or observations made by James Webb Space Telescope that may strengthen or weaken the current model of stellar and galactic formation in the early universe?
Yeah, I think almost every day it seems like we're finding new discoveries that were a surprise. I guess all discoveries are surprises, but some more so than others. So we knew we'd be probing the very first galaxies. And so, yes, in terms of stars and galaxies, big and small scales, certainly looking in the infrared at protoplanetary disks, stars in our own galaxy that are forming, remarkable work being done there. But then at the other extreme, looking at the galaxies, as I mentioned, the biggest surprise so far is to find massive spiral galaxies when the universe was just 500 million years old. And we just don't have models to reproduce that yet.
Thank you. Now, I have 2 questions here from lovely Jane Lopez. Does the type of galaxy change depending on its age? For instance, does a spiral galaxy change into an elliptical galaxy over time?
Thank you. Yes, galaxies do change over time depending on the conditions. So a spiral galaxy will never become an elliptical galaxy unless it merges with another big galaxy. So Andromeda and the Milky Way will become a big elliptical galaxy, but a spiral by itself will not change into an elliptical. It can't, because we've got motions in a disk, and there's nothing that's suddenly going to make the stars pop out in 3 dimensions.
Thank you. So the other question from lovely Lopez is, if there is a relativistic correlation between velocity and redshift, does it mean that the further the galaxy is from us, the faster it is moving away from us?
Yes.
Because of the expansion of the universe. Where are the galaxies moving into or onto?
Yeah,
where are they moving into? Yeah.
Oh, right. The first part of your question is absolutely right. Galaxies are moving away from each other because of the expansion of the universe. The second part has no meaning in the sense that it's space that's expanding. So you don't want to think about space as a grid that galaxies are moving through. Think of it as a grid where galaxies are on the intersections of the grid points, and now just expand your graph. So that's the expansion of the universe. And so it's not that they're moving into or away from something. Everything initially was at the same infinitesimally small point when the universe began, and then space grew.
Okay, thank you. This is a question from Joel Ferrier. For the double and chain galaxies, how do we differentiate them from gravitational lensing distortions?
Yeah, that's a very good question. And in fact, when I was first looking at chain galaxies, some of my colleagues are saying, are you sure that's not just a gravitational lensing effect of something? But we could rule that out because of what they were near or weren't near, and there were simply no galaxies or clusters of galaxies nearby that could have caused those distortions. As I'm sure you're aware, given your question, Webb is finding beautiful gravitational lensing effects, pushing our observations of very, very tiny, maybe even the first stars, individual stars and tiny, tiny galaxies because of lensing, and Hubble did a lot of lensing work as well. But these are in isolated fields where there couldn't be that effect. It's a very good question.
Okay, thank you. And here is a question from Thomas Encarnacion, another question from Thomas Encarnacion. In the event of merging galaxies, will there be stars that gets ejected and don't belong to a galaxy?
Fun question. Yeah, there are runaway stars, and we know that there are runaway stars from the Milky Way too, and so that can happen. Even without a merger, you can have stars that are interacting in such a way that you can have a star from a binary pair that gets on an orbit that flings it out of the galaxy. Certainly in mergers that can happen too, and so you're going to have most of the stars that are going to merge, but randomly some of them are going to end up being on orbits that will carry them out.
Thank you. So I'll read the last questions here. How did scientists determine that the Milky Way is a barred spiral galaxy?
Oh,
Did
that's
they
an
take a
interesting.
selfie? Yeah.
Yeah, no, that's an interesting. That's a very good question. And so that is a lot of painstaking work having to do with measuring distributions of stars and trying to figure out what our structure is, and realizing that based on velocities, trying to constrain exactly where the distances are, it just turned out that there's about a 2 kiloparsec, about 6,000 light year bar in the center of our galaxy. So it's just by very painstaking measurements of distributions of objects. The spiral structure in general of our galaxy was first understood looking at 21 centimeter emission of hydrogen atoms, so looking at the gas distribution and then trying to correlate that with where all the stars were. And so it's a very slow process over the years of just mapping out where things are.
And related to the Milky Way, what is the ultimate fate of our Milky Way galaxy?
Going to be an elliptical along with Andromeda.
Okay. And this is again in relation to the James Webb Space Telescope. In February, it was announced that the James Webb Space Telescope discovered a half-dozen galaxies that formed between 500 million and 700 million years after the Big Bang, that are more massive and more mature than expected. How does this finding impact existing theories about the evolution of galaxies and the age of the universe?
Yeah, those were the half dozen whose pictures I showed is little red dots. And so massive in this sense means billion years, billion solar masses within the first half billion years. Our models don't reproduce that. Now, to me, it sounds like what needs tweaking, and again, I'm not doing the simulations, but it sounds like what you need are just randomly overdense regions in the very early universe. And because everything is driven by gravity, that's why regular galaxies have so much gas today. They don't have much mass, and so the star formation happened more slowly. Ellipticals used up all their gas right away to form stars. So what we need is conditions where you build up a big disk very early on, and that's going to make massive star formation early on with a lot of turbulence, generating very high mass complexes within that. And so somehow you need to randomly be able to have some especially dense regions very early on. And so I think it's not a big leap to be able to do that, but the simulations just haven't had all the knobs tweaked to get really overdense structures. Just they have sort of randomly clump, 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 clump. And we need to have within the model some way that randomly you're going to get big clumps right away. I don't think it requires new physics or anything like that. I think it's just a matter of looking at the density distributions, and those are random, and just tweaking that.
Thank you. This question is from Don Godi Lorica. How do you prioritize what direction to look at using the James Webb Space Telescope?
Oh yeah, that's a great question. So astronomers have a chance to apply. Anyone can apply once a year. And there's committees of peers that review all the proposals. So it's a massive effort of hundreds of astronomers reading thousands of proposals and ranking them. And so the goal is to have a distribution of different kinds of science, from protoplanetary disks to stars to galaxies to cosmology, all of that, but to pick the best science. And so it's really peer reviewed, and the oversubscription rate is about 10 to 1. So for every 10 proposals you submit, you might get one accepted, because there's just a limited number of hours that you can observe, but it's all done by peer review.
This is for,
Oh, and let me just add,
Yeah.
what's beautiful about Hubble and Webb is that all the data become publicly available ultimately. And so you or astronomers, anyone can download the data. So even though you might be the one who leads the principal investigation of an object, all that data is for everyone later. So even if you had a proposal that wasn't successful, you might find in the archives exactly what you wanted to look at that someone else happened to observe.
thank you. Going to the last, there are several questions still remaining, but I'll try to read them again. This one, I think you also touch a little bit on the question from Bim Keros Bandilia. On what space does the universe expand into?
Right. It doesn't. And so it's space itself that's expanding. Unless you want to get into multiverse theories, which I won't go there, except to just say, as I'm sure you know, there are some models that say our universe is just one of many. Think of Men in Black with their marbles that are the universes. And so in some theoretical models, you could have an infinite number of universes with different physical constants in them. Some of them come and go very quickly because the constants are such that you don't end up getting stars or you don't end up getting life. But and so in that sense, you could imagine that our universe is in one spot in a super universe. But that's beyond our observations. It's all theory and fun science fiction. But otherwise, space itself is what's growing.
Maybe this is also related to the question by Alvin Lopez. What are your thoughts about Roger Penrose's cyclic hypothesis of the universe arising from pre-existing universe and so on?
What are my thoughts about what?
Roger Penrose's cyclic
Oh.
hypothesis of the universe arising from a pre-existing universe and so on.
Right. All of these questions I think are really fun and fascinating, and I think right now they're at their very infancy in being able to really do any kind of measurement to verify. And I think that science is all about having a hypothesis that's testable. And so you get data and you refine your theories. And I think a lot of these multiverse theories are simply not testable things yet. So I think they're intriguing ideas. And although some multiverse people think that you might see evidence of a collision of a universe with another universe with some imprint that's in some cosmic microwave background or something like that, I think by and large these are not testable yet. So for me, they're intriguing, but not quite at the level of being able to do science with them yet.
Thank you. Another question about the merging of galaxies from Shirley's Cordero. It was mentioned in the lecture that the merging of the Andromeda and the Milky Way galaxy would cause the sky to be dominated with light from the stars and affect our visibility of outer space. Would that mean that it would also get hotter? How chaotic is the merging of two galaxies in general?
Yeah, that's a great question. Wouldn't get hotter any more than we get starlight, and the starlight heats up our planet, so that's good. But these stars are not going to be anywhere near ours. So the stars are separated, so stars don't get affected by the merger. It's the gas clouds that are going to be affected. Stars are still separated like pennies separated by city blocks. I mean, they're not near each other, so we're not going to have an increase in the heat. It's just that they're going to be a concentration of stars that is going to make our sky very bright. So let's see. So in general, if you were in a galaxy and your parent star was not in its old age, so if we were not a giant by the time the merger took place, which we will be a giant star by then, but if we weren't a giant star, so the Earth still existed, and our star still existed, then we would just notice a change in the brightness of the sky over a long time scale for the merger of hundreds of thousands of years. So yeah, otherwise it's just the overall structure that would appear different to a distant observer in our galaxy.
Thank you. This is from Martin Joy Irog. Not sure if this was already discussed previously, but I'm asking just in case. Can you explain what is the role of dark matter and dark energy in the formation and evolution of galaxies.
Yeah, dark energy. Yeah, good. Which I didn't mention, dark matter. Yeah. So we believe that if you look at the energy budget of the universe, because mass has an energy equivalence equals mc squared, then the universe seems to be about 3/4 dark energy, which we know essentially nothing about, and about 1/4 dark matter, which we know very little about, and a few percent of normal matter, which is most of what astronomers think about and work with. So so with these large-scale surveys that are being done by looking at big regions of the sky, we're starting to understand the distribution of dark matter and dark energy ultimately. And part of this will be with the Vera Rubin telescope, the formerly known as the Large Synoptic Survey Telescope, which will see first light, I think, next year, which will start to map out the sky every few days, looking for objects that vary in position or brightness, but also doing large surveys of the whole sky. And so the idea is that if you look at very distant galaxies, someone already mentioned gravitational lensing. If you look at an object behind a galaxy cluster, then its light will be distorted by the mass of that cluster. And by looking at individual galaxies at great distance across the sky in a big survey, statistically, you can model how their expected shape has changed because of going through intervening dark matter, which has a gravitational effect on the light. And so, in other words, if you're looking at galaxies, you expect spiral galaxies to have a certain distribution of inclinations and orientations. And so you see some viewed from the top and some viewed from the side. If they're lensed, then they're going to have some distortion that's built in. So it's very heavy on the modeling part of how much mass does it take to distort light from the distribution we would expect the shapes to have. And from that, you can generate these long tunnels of dark matter through the sky in different directions that show you that distribution. And dark energy would also play a role in affecting the statistics of the shapes. So, so I think we're learning, and of course that's coupled with what's going on with CERN and the super colliders trying to model elementary physics from the small scale physics side. And so I think the combination of those efforts will ultimately tell us more about the distribution of dark matter and dark energy, and hopefully combined with models in the lab or experiments in the lab, we'll be able to figure out what dark matter is. And dark energy, I think, is further behind in understanding what that is. But certainly it seems to dominate what's going on in the universe.
Thank you. And here are two related questions from Carl Santisteban. Is there any way to study the stars and galaxies outside of the observable universe? And number two from Danifeli Gulia. Is it possible that a galaxy outside of the observable universe will enter our range and be able to observe it?
Yeah, so no and no is the short answer. So if an object is beyond our observable universe, then that means that there's no way for the light to get to us. That it's so far away that in the lifetime of the universe, the light cannot reach us. And so if a galaxy is beyond the observable universe, and so you'd have to imagine some event where it suddenly got a enormous boost of energy that kicked it flying through opposite the expansion of the universe that had it somehow heading towards us. So that's not a physical event. So yeah, no, once the universe is expanded, then we're going to lose contact. I mean, ultimately, the very end of the universe, if it still keeps expanding and accelerating, is that we're all isolated from all other objects.
This is a more personal question. How does it feel to use the James Webb Space Telescope, the world's largest and most expensive space telescope?
Oh, it's really fun. I think most astronomers act like kids when they talk about Webb, because it's just so cool. I for one am still amazed that it actually worked with 400 points of failure, and it all worked. and I just think it's a remarkable achievement. I had the same thrill with Hubble, I must say. And back in the day, 40 years ago, when I was on mountaintops and using the 200-inch telescope, it's the same thrill to think that we could make an instrument on Earth whether it's still on Earth or in space, to figure out something about objects so far away and tie us to this grand universe. That's the thrill of astronomy for me. That's why I do it. It's a visceral feeling. So whether it's Webb or Hubble or a ground-based telescope, it's a similar thrill to me to be able to. So I think it's an engineering marvel that Webb exists and works. But I think each step of the way over the past 100 years of galaxy studies, I've been just blown away by the brilliance of people who are figuring out clever ways to look at things that are so remote.
Thank you, Deborah. Thank you again so much for answering. Thank you so much for gamely answering all of these questions. Your lecture really generated this is the most number of questions that we've encountered our webinar. But before we end the Q&A, maybe we can ask our panelists if they have other questions as well.
Yes, Jet. I do have one question for Debbie. Debbie, earlier in your talk, you showed Edwin Hubble's classification scheme for galaxies. So in that tuning fork diagram, it showed ellipticals evolving into spirals and barred spirals.
No, not
So, go ahead, finish your question, and then
yeah, my question is how do irregular galaxies fit in this?
Right. Good question. So the first part of it, yes, this tuning fork was never meant to be an evolutionary sequence. And so even though it's drawn with ellipticals on one side and spirals on the other, he never intended people to think that ellipticals became spirals. Early on in the thinking, people were wondering about that very thing. Do you start with a ball, and the ball flattens a little bit as it spins, and as it flattens, it can make a spiral arm, and the spiral arms come out. But by the time he put that diagram together, people were not thinking that. So it's not meant to be an evolutionary diagram. It's just sorting out ellipticals and spirals can have bars or not. Now, he didn't deal with irregulars. The only irregulars that could be seen with his telescope in those days were the very nearby ones. And so there were a lot of these little bitty things, but he didn't consider them as important as looking at the mass-dominated ones, the ellipticals and spirals. So if you were drawing a modern day tuning fork, you would put the ellipticals at the far right end. So you'd have the ellipticals, which can be both the most massive and the least massive objects in the universe, but you put them at one end, and then you got spirals, and then you got the regulars. And so yeah, there's a lot of work being done to say, well, what if we incorporate those, and then looking at particular types of galaxies, and how the dwarfs might evolve depending on what star formation. But that's a detail that, yeah, Hubble didn't work on that.
Oh, so you mean the tuning fork is mainly for classification according to morphology?
That's right. And so it's tied to the star formation history. So the ellipticals, which are hardly spinning, used up all their gas early on, so they're red, and they're essentially not rotating. The spirals are rotating between 100 and 400 kilometers per second, depending on their mass, with the galaxies with big bulges rotating faster than the smaller bulges. And that affects their star formation history because they're spinning faster, then they're using up their gas more early on. So the spirals that are spinning faster are a little bit redder and a little less star formation than the galaxies that are spinning slower. And that's tied into regulars, which are very slow rotators. They're fat disks. They haven't had much star formation, so the disks are still puffy. And so they're only spinning at like 50 kilometers per second. So they've got a lot more star formation today because they have less gas. So it is a sequence of spin rates and gas consumption rates and colors, therefore, that are reflecting when they first started forming most of the stars and how much they're forming now.
Great. Thank you.
Sure.
Thank you, Edwin. Any other questions before we end the
Jet, mine
Q&A?
is not a question,
Okay.
but I just want to say a big thank you to Debbie for really doing this.
Yeah.
Despite all the work she does in research, she took her time to explain to us and enlighten us, basically, a lot of us on about galaxies.
Well, it was my pleasure, Imelda, and I thank you so much for inviting me. And it's just wonderful to see you again. And to all of you, congratulations on your efforts. And I'm thrilled that so many people joined to hear about galaxies. And I hope I answered some questions, and I enjoyed having you present.
And by the way, Debbie, you have a book on the galaxies, right? I saw it in Amazon.
Right.
Yeah.
In the whole book. Yeah.
Yeah, I believe Imelda has a copy of it, right, Imelda?
Yeah, it's a textbook I wrote for undergraduates back in the late 90s, and a lot of the basics are still the same. You still got basic descriptions of galaxies. Of course, the later chapters dealing with cosmological and there's nothing incorrect there. It's just that our ideas have evolved so much in the past 20 years.
Yes, to answer your question, Debbie is such an authority on this that she wrote a textbook on galaxies.
Do you have already an updated version of it, Debbie? Are you writing an updated version? Not yet.
No. I had no time to do that. That was a moment when it happened to work, but yeah, no plans. Other youngsters can carry on and update what's going on in the galaxy world far beyond what I can do.
Thank you. So if there are no more questions, I think we have taken enough of your time, Debbie. So I would like to take this opportunity to present our small token of appreciation from the Astronomical League of the Philippines.
Beautiful.
Yeah, and this certificate from the ALP is presented to Debra M. Elmegreen, Ph.D., for her invaluable insights, experiences, and expertise shared with the participants of the online talk entitled, A Glimpse of Galaxies at the Dawn of the Universe, held as part of the ALP Astronomy Expert Speaker Series of 2023, given this 20th day of May, signed by Mr. James Webb, President, and yours truly, Jose Francisco Aguilar, Vice President. Thank you, Debbie.
I will treasure it. Thank you. Thank you.
I'll send you by email also a copy, and
Thank you
if
so
you can
much.
send a paper, a hard copy version.
Oh, that's really sweet. Thank you.
Thank
Appreciate it. Thank you all. Bye.
Before we end, may I ask James, is it okay,
Okay.
Debbie, if we take a group picture?
Oh, sure.
Yeah.
Okay, look at that picture, Peter. Jet, can you adjust a little outside?
Yeah,
Yes, that's it. Wait. 1, 2, 3. One more. 1, 2, 3. Okay, thank you.
Thank you so
Thank you.
much.
Thank you very much, Debra,
Take care.
for
Thank you.
accepting
Thank
our
you.
invitation.
My pleasure. Thank you.
Thank you.
Thank you,
Thanks,
Deborah.
Debbie.
Bye.
So before we conclude today's webinar, I would like to thank all our attendees for joining us. Of course, we have a record number of attendees today. And we will be sending you your certificate of attendance by email for all of you who were able to join us. As mentioned earlier, this is part of our ALP Astronomy Expert Speaker Series. We had one in 2022, and we also have in 2023. So we started this webinar last year, and we have I have not updated this, but like James mentioned, we're also continuing with this webinar as we for the next months for the entire year. So we can never thank for all our speakers. We can never thank you enough. And these webinars, for those who want to get a copy of the lecture, this will be
Uploaded.
uploaded in our official ALP YouTube channel. Yeah, as shown here. And for our upcoming online talks, I'm happy to announce that on June 24, that is a Saturday, Brother Robert Mackey, the curator of the Vatican Observatory Meteorite Collection in Castel Gandolfo, Italy, will give a talk on the science of meteorites. So we will announce the final date and time soon. And to be followed by another by a talk by Brother Guy de Gonsalmaño, the director of the Vatican Observatory, and he will talk about exploring Pluto and the Kuiper Belt objects. And this will be either on July 15 or July 22, and please wait for the announcements. So thank you everyone for attending. Take care and clear sky always, clear skies always. And for the panelists, I will be posting the Zoom link for our post-webinar meeting. Thank you everyone. Good night.
Thanks, everyone.
Thank
Thanks,
you.
Dr.
Thank you.
Dr.
Thanks,
Debbie.
Bye.
Thank you,
Bye.
everyone. Bye-bye. Bye, Elmer.
Bye.
Bye-bye.
Bye-bye.
Bye. Bye, Doc.
Great. Well, great to see you all. Thanks again.
Okay,
Bye.
bye-bye.
Everyone. Thank you.
Regards to
Congratulations.
Bruce.
Thank you, Elma.
Yeah, regards to Bruce.
Okay. Hey, Bruce, are you here?
Oh, that would be nice if you're there.
He can show his face. The panelists are just left now, and Milda introduced me with talking about you. So there he is.
Hi,
Hello.
Bruce.
Hi.
Hi.
Bruce.
Can we take another shot? Can we take another shot with Bruce also?
Yeah.
in?
Yeah.
Yeah. Bruce, can you get closer to Elma?
Debbie.
Now we have the
Debbie.
disappearing thing. Yeah.
Okay. Ready? 1, 2. Wait. 1, 2, 3. Debbie, a little bit to the right, a little. Okay, that's it. That's it. Good. 1, 2, 3. Nice. Thank you.
Yeah, good.
Thank you so much.
Bye,
Bruce.
everyone.
Nice.
Good to see you,
Okay.
Good
Bruce.
to see you, Bruce.
Yeah.
Nice.
Okay. Bye all.
Bye.